let R be the region between the graphs of y equals 1 and y equals the sine of x. From this to that, what is the volume of the solid obtained by revolving R around the axis? All right, so sine function again. It's funny how that happens. I'm a pretty transparent person. I mean, we spent a good 30 minutes yesterday talking about sine graphs. If you leave the test on Tuesday being like, I can't believe there was a sine question on there, then I don't know. I don't know. I don't know how to drop hints any better than this. I mean, the sine function keeps coming up over and over again. I'm asking you to draw it repeatedly. It's going to be on the test, for crying out loud. You just got to understand the test now. But I have told you, your bailout is the calculator. Just make sure it's in radian mode. And it's not going to do you any good. If you put the sine function in your calculator, and all you get when you put your domain in, all you get is a horizontal line, you're in the wrong mode. All right? There you go. Word solidified. So the graph of y equals 1 and y equals sine of x on 0 to pi over 2. My big bugaboo is drawing lines, apparently. I'm going to exaggerate this. This is pi over 2. Here's 0. The sine wave hits its maximum at pi over 2. Here's y equals 1. I'll just kind of give it a little extra length. And give this a little extra. Actually, I'll change the color a little bit. All right, so we want to spin this bad boy around the x-axis. All right. If we spun it around the y-axis, it would be a disk method question. All right. The reason why is this region here, this little triangular region. Well, actually, depending on which region we're talking about. Right. So, if it were this region, then it would still not be a disk method question. But since we're talking about this triangular region here, if we were spinning it around the y-axis, it would be disk because this entire bounded area is adjacent to the y-axis. All right, so it would be disk because I can get from the axis to the curve without any interruption, kind of like areas. All right. In this case, I need to spin this triangular region around the x-axis. There's a big old gap in between the bounded area and the axis of revolution. That's a problem. Right? But it's not an insurmountable problem. Right? If the question were changed ever so slightly, if it said, on the interval of 0 to pi over 2, the area bounded between y equals the sine of x and y equals 0, so this region spun around the x-axis, then it would be disk, because I could get from the axis of revolution to the curve without any interruption. But just thinking about this curve here, if I need to spin this around the y-axis, there would be a gap. It's interrupted. All right, so then it would be washer. All right, so you're thinking about, can I get to the outermost part of the bounded region in one straight shot? Yes, disk. No, washer. All right, so how do we handle it? We subtract. You need two arbitrary rectangles. One to account for the outermost part of the bounded area. And one to account for the inner part of the bounded area. And you put it anywhere you want, but they could coincide with one another. AKA, the purple one could be right on top of the blue one. And in fact, that's actually how it would work. I would start with a blue rectangle all the way at the y-axis with a purple one overlaying it. I'd find the volume as I spun that around and subtract the volume as I spun the purple one around. Then move over a smidge, do the same thing, spin the blue one around, get its volume, spin the purple one around, get its volume, subtract, and so on. all right, all the way from 0 to pi over 2. But this was tough enough for me to draw as it was, so this is where I stopped. Anyway, what I want to do is I want to apply the disk method for this rectangle, and I want to apply the disk method for that rectangle. So, really, in my opinion, there is no such thing as the washer method. It is the disk method for a different situation. All right? I mean, like, if you add something twice, like, I have 2 plus 3, and then I add 4. Is it no longer called addition? Do we have to come up with a new name for it? No, you're just doing the same thing a second time. What does it matter? Right? It's the disk method. It's just we're doing it twice. All right? The difference is that the disk method here, for the purple one, is going to help us find the volume of the part that we don't want. All right? So if I were to spin this blue rectangle around for all values between 0 and pi over 2, I'd get a cylinder, because this line would go, and it would be stable all the way through. It would be parallel all the way through. So it would create a cylinder. What the purple one does is it bores out the guts of that cylinder. Kind of like if you're spinning around on a pottery wheel, you put the clay on there, you get the wheel going, and then you start pulling out the guts. You hold your hand in there and let the, actually, which way does it go? That way? Damn it. Yeah, but the pottery wheels they go clockwise, right? Yeah. So then I'd have to put my hand like this, and all the momentum would pull it against my hand, and then all that clay would come out, and I just scoop it out as I go. Right? So that's what's happening here. The purple one is the hand that's boring out the insides of the cylinder. All right. So what does that mean after all of that? 7 minutes of me saying all that stuff? It means I need a pi r squared and another pi r squared. Okay. Well, this r is constant. That radius is 1. I mean, I could call it y if I want, but y is 1 for all values over this interval. It's not changing. Shockingly, I actually drew a straight horizontal line without using a line drawer. The other one is variable, so that one I will call y. So, on the interval of 0 to pi over 2, I'm going to have a pi r squared with a thickness dx. From that, I'm going to subtract on the same interval another pi r squared, also with thickness dx. All right. The r for the first rectangle, because it's not variable, I just chuck the 1 in there. One shot. For the purple rectangle, depending on where I am, it's going to be a different value, but always sign depending on what x is. Right? So sine of x goes in the other integral. So pop that in your calculator, call it a day. Now, my questions always say, when it comes to the situations where you don't actually have to get an answer, this one says find the volume, right? What is the volume? But if it just said find the answer, this is a cylinder, right? If I spin y equals 1 around the x-axis, it's a cylinder. Write an integral or sum of integrals. All right, well, here's the integral that you need. This is a luxury. It's up to you. Pi r squared h if you want, right? The radius is 1. Pi times 1 squared times the height of the cylinder, which would be the distance from 0 to pi over 2. Okay? This is constant. It looks fancy, but this is just pi. Remember, when we're finding the antiderivative of a constant function, take that constant and multiply it by the difference between the bounds. Pi r squared h. All right? So whether you write it as an integral or you do it geometrically, you have it, right? So you really can't go wrong in that regard. In terms of the calculation, it's pretty quick, I guess. Before we do that, though, because I just realized that I changed my notes to include a general rule, so we'll actually get to the point where it's a general rule. You'll notice that the bounds of integration are the same. Both cases involve a pi. The only thing that varies from one case to another is the r squared part. So this could be simplified down to 0, or the integral on the interval of 0 to pi over 2. I pull out the pi from the whole shibiggity bang. We're going to have 1 squared minus sine squared dx. All right. That you can put in your calculator. I mean, you can simplify it if you want. I mean, because it ends up being 1 minus sine squared, which is cosine squared. So it's a little bit nicer, but this will be a little bit cleaner. But I didn't do this to make it easier to put in my calculator. I'm going to show you something in a sec. I'm just going to crank this out right quick. Just making sure I'm in the right mode, which is, of course, a radian mode. I don't know if I mentioned that tonight. About 2.467, approx. All right. So the general rule ends up being pi on the interval of a to b, r squared minus r squared, d, well, something. All right, capital R, lowercase r distinguishes one radius from the other. The idea being that the capital R represents the radius that's further away from the axis of revolution. The lowercase r is the radius that's closer. I left this open because it could be revolved around a vertical axis or a horizontal axis, so it could be a dy or a dx. All right, so it could be one or the other, but you can kind of chuck it right in and go from there. But like I said, I mean that's a general rule for the washer method, and it's great, it's wonderful. But I don't believe in the washer method. I don't believe it's a method. Honestly, I feel like it's, I didn't research this, so I'm just speaking out of school here. I feel like whoever came up with the disk method, like did the real work, and then somebody else came like later and like built off of that work. Maybe it was, I kind of imagine it was like the assistant, the annoying assistant that like doesn't really do anything. And it's like, Eureka, I came up with the disk method. Can you believe this? Well, I came up with the washer method. And like, that's really all it was, because it's like the same thing, right? It's a slight adjustment to it, right? So if you know the disk method, you really know them both. Disk method plus common sense, all right? So the next example follows the same general idea. The key to this one is, oh, look, a typo for someone. The region enclosed by the graph of equals x squared. Well, I would imagine that's supposed to say y equals x squared. So that's for somebody. I think there's 2 people maxed out. 3 people maxed out now on typos. So y equals x squared. Yeah, people getting maxed out is good for you if you're not. That means that the people that are that have quick trigger fingers, they're out. You don't have to worry about them anymore. So if you get a typo, then you can feel free to just go for it. I've noticed that some folks like to wait until they get home and really sit down and, like, you know, maybe get dinner on the table, relax, put their feet up and say, I'll send out a couple of typos right now. It's too late when you do that. Somebody sent me, you know, I don't mean to make anyone feel bad, but somebody sent me like 3, 4 typos. I think it was 3. I was only able to give credit for one of them because the other 2 were already claimed. Right? So if you're at the point where you're making a well-crafted email to address typos, then you're probably too late. So, remind. Remind's the best way to go because that's boom. Right? So, and I've had people. I mean, I don't know that I'm this savvy, but they'll just take a quick picture of it and then send that in. So it's like, boom, that's in. And then they'll send a follow-up saying what the problem was. I'm fine with it. Like, you have the timestamp, you're the winner. All right. You could go the next step of, marking it up, like on your phone, like circling it, pointing to the part that's a problem, and then sending the picture in. That's fine too. Like, just whatever it takes. And again, if you send in typos, check Blackboard. If you haven't received credit after like 24, 48 hours, it's not because I didn't get it. All right? It's because you didn't get it. Or somebody beat you to it. Right? So here's one for somebody. So let the feeding frenzy begin. The region enclosed by the graph of y equals x squared. The best is when there's a typo on a unit test, and there's not a damn thing you could do about it, because the minute you pick up your phone during a test, you just got a 0. So it's like, oh man, I need this typo, but I can't do it. And now you got to remember and
rush to finish the tests.
Yeah. It's like you turn in a test and you get a solid 2 on it just so you can get a typo bonus point. This looks weird. I like the feeding frenzy. Yeah, there we go. It's coming in hot now. All right, so y equals x squared. The line x equals 2. And the x-axis is revolved around the y-axis. So that's implying that I only care about the first quadrant. Spun around that y-axis right now. I feel like I'm getting a bloody nose. So anyway, so spinning it around the y-axis, you can see that there's a gap between the region that I'm spinning and the axis of revolution. Right. So I need a rectangle to represent the outermost function. And a rectangle to represent the innermost. Thickness is in terms of y. Now I just need a measure for those radii. All right, one of them's easy. I'll use the little shortcut formula there. Now, we're going, in terms of y, from the x-axis, which is at 0, to the intersection of the two functions, which would be 4. I'm only getting that just by chucking the 2 into the function. 2 squared is equal to 4. All right, so I have my bounds. Really great to hear all the people's future plans and stuff, their thoughts about the state of the world and campus as they're yelling at the top of their lungs walking by a class that's in session. It's all right. All right, we're good. No, that's cool. That's the first time anybody ever apologized. They're usually like, haha, they're suckers, we're out of class. So the outer function, constant function again. Oh, I loosely use the term function. That line is not a function, but the length of the radius is a function. All right, so 2. Now I just need the radius that would represent the distance from the axis of revolution to the curve. Right, that represents the part of the volume that I don't want. All right, distance from the y-axis to a point in space is x. All right, we know that y is equal to x squared, which means that x is equal to the square root of y. And so that would be my radius. And this one would not be terrible if I had to do it by hand, because you square the radical and we're good to go.
Can you just explain why the 2 goes first and the square root of y goes second?
Because you're looking for the outermost part of the bounded area. That's what's going to get spun around. That's the part that you do want, the outermost part of the solid. The red part is what you're going to gut out of the inside.
Oh, so whatever's furthest away from the x-axis goes first?
Not always the x-axis. Whatever is furthest away from the axis of revolution.
So whatever's furthest away from what's being rotated goes first, and then what's inside goes second?
Exactly. No problem. Okay, so